In this video you will see how we go from a carbon sheet to a Formula 1 race car.
How do you design a race car? How it's built? How it's developed? What does the wind tunnel look like? How is the carbon fiber processed? I'm about to take you on an unprecedented journey inside the world's leading race car factory, Dallara. I had the privilege of entering its offices close to the public to show you some of their secrets. Just sit comfortably and enjoy, because you will discover things you've never imagined, and you'll find out everything behind supercars and racing cars.
Our journey starts here, from the history. What is Dallara?
Dallara is a name, in fact a last name, that of Giampaolo Dallara, born right here in Varano de' Melegari, Italy, on November 16, 1936. He graduated in '59 from the Politecnico of Milano in aeronautical engineering, and he began working at Ferrari. Then he moved to Maserati, and shortly after he contributed to the birth of Lamborghini Automobili, helping Ferruccio Lamborghini, its founder, in the development of the first Lamborghini cars.
And I want to tell you the history from here, from the ramp. This is a car exhibition inside Dallara, which anyone can visit. You can come here and see live all the cars. And you can see how the cars are placed like in a starting grid. And the first one in the starting grid is the Lamborghini Miura. The safety here was not that much, considering the rigid steering wheel column and the fuel tank in the front with the battery down the fuel tank. Yeah, the word safety was not really the most important word for this car, but it represents the pioneeristic era of motorsports.
And after contributing to the birth of Lamborghini, in 1972 Giampaolo founded his own company, right here in Varano.
So this is the SP1000, the first car ever made by Dallara, and you can see two things. First of all, the whole bodywork is just one piece of glass fiber, and we have 3 seats. And you may say, why? Because the regulation of that championship stated that the car should have 2 seats, and Dallara said, okay, let's make 3 seats so that the driver is in the middle and the weight distribution is better. The problem with this car is that it was so competitive and so fast that it won so easily that the following year they changed the regulations. And then this car, the X19, made a change in the history of Dallara, because from this car, made in collaboration with the Fiat Group, Dallara started to create, design and produce cars in collaborations with other brands. For example, here we have the Lancia Beta Monte Carlo and the Lancia LC1, which have been designed and produced in collaboration with Dallara, and they actually have been produced here in Varano. 640 kilos for 480 horsepower in 1981. Was that even legal? I mean, 340 kilometers an hour. The first Formula 3 who won the Italian championship, followed by the first Formula 3 full carbon. You know why I say that a car is like a human being? Because usually, to build a car like this one, from the first scratch until the car is ready, it takes around 9 months, you know, like the human being. This car was made in 5 months. You may say, okay, it was made in a hurry, so it might not be that good. Well, the thing is that it was so good that they have to remove 100 horsepower because otherwise it would have been too fast. Gilles Villeneuve. This is a very iconical car because this is a Can-Am that Gilles Villeneuve used for the first races. And apart from the Can-Am series, which is something that gives me goosebumps, I want to show you some incredible mechanical engineering solution to provide the dust to enter into the carburetors. Yeah, tennis balls. Yeah, simple yet effective. But what I want to tell you about this car is not just the magic behind Can-Am, but also the lack of safety that these cars used to have. Because look at this, the fuel tank's close to the driver. And those were years where the safety was not the most important thing, but the performance. And then from those years, the motorsport evolved so much that we came to this, the Formula 3 that saved the life of Sophia Flores in one of the most horrific crash in the motorsport history, where the driver came out alive, and it was just thanks to the incredible development that Dallara did on these cars. it's so good to watch this car, this GP2 car. I mean, is it just me that watched this car and fell in love with it? Tell me, is it just me? Who plays Gran Turismo? I do recall this car, right? This is the KTM X-Bow, which has been designed and produced by Dallara. They produced the first 100 of these cars, and the 100th has been gifted to Dallara from KTM. And then we travel far away from Italy, because this is the Super Formula, which races in Japan. This is the first Dallara car who won the 500 of Indianapolis. And behind there is another Indy car. And you know, right, that today all the Indy cars are made by Dallara. And also all the NASCARs. And also the Formula 2, the Formula 3. And the list is long. You don't hear this car coming, but you see it. Because this is the Formula E, the electric car, the Jane 2. And I would love to tell you that this car is totally made by Dallara, but I can't tell you. I'm sorry about that. So the thing is that they told the designer to make a diffuser, but they didn't tell them how long. And so they did this huge diffuser. And this car won just 4 out of 5 24 hours of Daytona, and it's the evolution of another car down there, which was the first car by Dallara who won the 24 hours of Daytona. I don't know what to say anymore. I'm just speechless. Oh, man, that's insane. I'm gonna show you how it looks. So this is what you see. Do you understand what I mean? Mamma mia. There are the keys. I wanna turn it on. So how could I not finish this walk through the history talking about the queen of motorsport, which is the Formula 1. You will see here 30 years of evolution, because this is a 1988 Formula 1, totally designed and manufactured by Dallara. This is the car on which raced Alex Caffey. And the thing you can notice is there is almost no aerodynamics. Okay, there are the front and rear wings, there is the floor, the diffuser, but nothing more. It's just a piece of metal with a huge and too much powerful engine and 2 big tires. And then we get to this, the 2018 Formula 1 AS racing team. Look at this, look at the complexity of their aerodynamic of this car. Look at all these tiny pieces of carbon, each one of them has a specific purpose. Look at this, on the halo, you have these tiny things that do something with aerodynamics. And later we will ask to Dialma, the chief aerodynamic engineer. I really don't know what to say, apart from the dimension of this car. I think it's the biggest car ever made in motorsport, but the complexity is just astounding. Well, actually, I lied to you, because there are 2 more cars in this ramp, which are the 2 Dallara Stradale. But we will see them in detail, because I will make a detailed video about them, showing you the production and driving it in first person on circuit. And what is today Dallara? Dallara has 3 main headquarters. One is in Varano here, where you have the development, the aerodynamic building, the research center, the testing, and the production of the Dallara Stradale. And then we have another headquarters in Collecchio, which we will see later, where they produce on big scale the components. And then we have one headquarters in Indianapolis in the US, because you know, some of the most beautiful and performing racing cars in the US are made by Dallara, so they have an headquarters there. And I forgot to mention one thing, that here in Varano there is the university. The university? Yeah, inside Dallara there is a university. And from the classrooms, students see the ramp with all the cars on display. So, this university is nothing more than one of the Muner specialized courses. And you probably never heard of Muner. It stands for Motor Vehicle University of Emilia-Romagna. And it's a collection of university courses here in the Italian region. But the question is, why do we have a university inside Dallara? That's because in Dallara they noticed that students are generally prepared, but they were always missing something to get into the business.
So they created this graduate program to teach them all those things. And just think that the person who teaches aerodynamic classes here is the same person who designs Formula 1 cars today. This course has 25 places per year and lasts 1 year, which is the last year of master's degree. So you may think it's going to be very expensive, right? Do you want to know how much it costs? Do you really want to know? This course costs zero. Exactly, it's public university. Dallara makes its facility available to the university for free. And then many of the engineers who come out of the university end up working at Dallara or within the Motor Valley. But there is more than just the university. In fact, Dallara has built teaching labs for middle and high school students, where every week students from all over Italy come to learn.
Let's start by saying that this activity in particular is not profitable for Dallara. And you may say, okay, why do they do that? Why do they invest in it? Well, first of all, this is what the visionary businesses do. But also, you can imagine that stimulating the passion into young people and providing them with knowledge creates brilliant minds that maybe in the future will come to work here. In the first lab, we studied the materials. So they created some experiments where you can visualize what happens. For example, here we have two cars, one with the metal nose, the other one with the rubber nose. So you can visualize the difference between an impact without absorption and an impact with absorption. Meanwhile, Alberto joined me. He's the man in charge of the Dallara Academy. And the next game is about the material flexibilities. Okay, we have 4 different steps where we can test the flexibility of materials. We start with the steel. And you can see that I have to apply 17 kilos to flex it by 3.5 millimeters. And then we have the aluminum, which is 69.7 kilos. Is the aluminum less flexible than steel?
Well, you can compare the two materials with the same force, and you have to apply more force in order to deform the same amount of millimeters.
Okay. The second room is about the aerodynamics, and we have a tiny wind tunnel in here. How does it work, Albi?
It works like a real wind tunnel, as it has a fan that generates a flow that goes from left to right. It happens as you put a hand outside the window.
Oh yeah, that you feel that the air pushing up, pulling up the air.
Yeah. If you rotate your wrist, you can actually differentiate the load that you can see on your hand. And this platform works the same.
Okay.
You can rotate the angle of the platform, and you can interact with the airflow.
In the third lab, my driver's ability will have a very important challenge because we have this simulator which simulates the effort that a driver puts in the drive. So it will test my performance in steering and braking, right?
Yes, it's a Formula 2 car. It's actually the real force that a driver has to put to steer at Lassigne in Le Castellet circuit. 3, 2, 1.
No power steering.
Yeah.
My God.
No driver assistance.
Guys, I'm used to driving NASCAR. I'm not sure if I want to find the budget for Formula 2. Okay, now the braking.
Yeah.
I'm confident with the braking.
Okay.
I'm done with this.
Yeah, this experiment, I think that shows pretty much the efforts of a driver. So it's an athlete. So
I am a driver, but the NASCAR is not like that. Okay, here we have 3 different seats, each of them which is put on a spring to simulate the suspension. And only in the last we have the damper. So what do we see? We see that in the first one, only spring, no damper, and we have to replicate the chart. Oh. While here, the second, we have a stiffer spring, which is harder. And in the last one, oh, we have the damper, which damps. Okay, I need a break.
And this is just the tip of the iceberg. Our journey has just begun. What you've seen so far is the part that is open to the public, which you can also visit if you come to Italy. In the description you can find the opening times. And this is exactly what you see when you pass through Varano de Malagari city. This beautiful building that was designed in 2015, started in 2016, opened in 2018, and here they also hold events, corporate incentives, art exhibitions, In the first year, they received 33,000 people and 200 events. Wow. Now, let's leave the part open to the public and get into the heart of Dallara. I told you at the beginning of the video that I will tell you how it goes from a carbon sheet to a Formula 1 car. Well, in the beginning, you don't start from a carbon sheet, but you start from a project, an idea, and the process by which that idea is born, I tell you into the aerodynamic park.
Welcome to the aerodynamic department. Now, I want to show you for first this model here. This is the Dallara Stradale, and if you look at it, you may say, okay, wow, look at this, they put this cool model like a piece of furniture, you know. And the thing is that this is the actual model that is tested in the wind tunnel. You probably thought that in the wind tunnel they test the real car. Well, that's wrong. That's what I thought at the beginning. So yeah, in the motorsport, the development is made on a small scale models. And I want to show you the whole process in order to let you understand how is a car developed. So we start from a concept and then we have to go to the real car. So what is the workflow from the concept to the real car? The workflow is made of two models. We have the mathematical model, which is developed and tested virtually on the computers. And we have the physical model, which is built in the real world and tested in the wind tunnel. So the first thing that is done when you have the concept is to build the mathematical model. So you create a virtual model, you give it to the computer, you do a simulation, you analyze the data and you say, okay, this is good, or no, this is bad. You roll back and once more you do the same loop until you have some consistent data. Once you are confident that what you've done in the CFD makes sense, you build the physical model, which then is tested into the wind tunnel. At this point, you can collect the data from the virtual test and from the real test. And you can combine them to see if everything is going good. Once you are confident that all the data you collected are good, the design of the car is fine, then you build the actual car and you test it in the real world. And that is the final validation, because all those models that you used to test are not exactly like the real world. They have some approximation. So those approximations need to be tested in the real world. Okay, so we came here upstairs to the first floor. I'm here with Dial Mazzinelli, who told me not to tell you, but he won twice the prize of the best aerodynamic in the world. Dialma, what do you do here?
In this floor, we run the first phase of the process that you presented on the floor below. So basically, now we are here running all the concept and development phase. Behind any closed door, there is a dedicated team of engineers and aerodynamicists running the project for one dedicated client. We obviously have to guarantee the best possible confidentiality to our clients.
Mostly all of the doors, we cannot get inside, we cannot show what's
yes,
there.
We cannot, but I can tell you what we are doing. So basically we are producing here files representing body parts. It could be, let's say, a small patch of the body. It could be a bigger assembly, as for instance, the front wheel assembly, rear wing assembly, or whatever. And then these files are run by CFD. We are in the CFD development phase, or they are run, let's say they will be part of the physical model that will run in the tunnel.
So that's why the model that I saw below, it's like a puzzle. It's made of many different parts. So you design every single part and then...
Any single part, keep in mind that our model is composed by nearly 500 components, and each component is designed here, as well as all the CFD assemblies.
So I think this is the only office where we can, where we can enter. Guys, can you imagine? All these doors are top secrets. We cannot get inside.
Welcome to the office.
The IndyCar.
We can show you, because this is a Dallara car. This is the actual car generation of the IndyCar series. And you can see the complete card of the model that you will, let's say, see in the model show below, and the relative CFD analysis. So we can, let's say, see that with a moving cross-plane, we can have the complete visualization of the flow field around the car.
So that's like an X-ray going through the aerodynamic behavior of the car.
And we can better realize what is working, what is not working. And this is the reason why I told you before that, let's say, all the initial phases run essentially in CFD, because you can very quickly debug, let's say, your study, unless correct maturity of your product is reached. Then at that point, we will, let's say, build up also the physical model.
Wow. I'm just speechless. With every door you open, you find things that you don't understand why. Look at this. This is used for cleaning and it's full carbon. Look at this. It's handmade. Look at the rivet here. This, it's not the handle, it's probably an air duct. They built it. So I came to film on the other side of the floor and they just closed this door because they told me you cannot know what's inside. Okay, they just closed also that door and they just told me that here it's made a big part of the development of Haas Formula 1 racing team. I would love to go inside and film and see, but I can't. I just can't. And they're just watching me. Look at there. They're watching at me, say no, okay. I won't do it. The thing is that, think about all the supercars and hypercars that you see on the road, okay? In many of them, there are some parts designed and developed by Dallara, but I can't tell you how many of them, which one of them, I just can't tell you, but I think that Dallara is like, you know, Batman. It's like a hero that works behind everything. You don't see it, but you know it's there and you know that everything works thanks to them. That's what it is. Okay, we saw how the virtual model is made and now we get to the physical model because, get ready, in a few minutes we will get to the wind tunnel and you see how it works. So, this is the history of the physical model. Do you remember the Formula 1 we saw in the ramp? The Dallara Formula 1, the Caffi drove? This was the wind tunnel model. It's made out of wood. This is the actual model that they used in the wind tunnel and this was the beginning of the physical models. And then the evolution came to the carbon. This is an Audi DTM from 2009 and as you can see it's full carbon. So you have the advantage of using the new technologies of the carbon. But there is a problem in using the carbon, which is carbon has many nice properties, but it has one major drawback, that it takes time to build the part. So for example, if you want to change a part of the car and test it in the physical model, it takes days to manufacture it, to cook it in the autoclave. We will see it later. So the evolution of the carbon model is this one. This is the technology that they use nowadays, and this is all 3D printed. All these parts, like a puzzle, are the files that Dialma was telling us earlier. So each one of them is designed in the first floor, and it may be tested in the CFD, or it may be 3D printed, put it on the real model, and test it in the wind tunnel. So all the parts that we saw from the model, like this brake disc, are 3D printed in this room, right?
Yes. We kept working with this technology in A1. Now we are equipped with 10 machines working full time, so 24-hour days and 7 days per week, and produces something like more than 50,000 components per year. So it's an essential asset for us and for all the motorsport community, because what is the advantage of this technology? This is surely not the cost, because finally expensive are the machines and expensive is the cost per unit of the racing, but what you can get in terms of efficiency of the process is much more. So you compress so much the time to test that this is the benefit.
So it's more expensive, but it makes you save so much time that in the end the advantage is...
you make the saving on the process. And you can see here how the process is done. So basically we are here, let's say, working volume, which is 500 per 600, full of liquid resin, and then there is a laser that is solidifying layer by layer with a typical step of 1/10 of mil. That section actually, for instance, is solidifying this cross section.
So this is the part that has been solid. So you mean all of that is a tank full of liquid resin, okay? And a laser is shooting only the part that needs to be solidified.
You will see soon a green light, that is the laser, yes, and this solidifying that section.
So it solidifies the part 1/10 of millimeter by 10th of millimeter, okay, going up, and then
finally you risk the level.
So the part will came out of the liquid resin.
Yeah, exactly.
How long does it take for that?
I can produce 30 of these brake discs per night.
So less than 1 hour, half an hour to make one part. Wow, and how much does the resin cost?
I would say $300 per kilo, so it's something. But again, the saving is on the process, not on the...
Exactly. So this is the IndyCar, and it's the same that we saw upstairs.
Exactly, and this is the 50% scale model of the existing car generation of IndyCar. And in this case, you can see that the chassis is in carbon, because it comes from, let's say, the initial years of this car generation. But you can see that in this car are, let's say, present all the developments that we did all along over these 10 years. Like, for instance, the windscreen, or let's say the front side plates, modification on the floor. So there is the history that IndyCar faced in the last 10 years.
So you use the same basis, like the chassis and everything, and then year by year you develop new parts to make the development
for performance, safety, or whatever.
Wow! And you told me, and that shocked me, that the model is more expensive than the real car.
Yes, sometimes yes, because the model is a prototype composed by 500 components that are 500 prototypes. So at the end of the story, the model cost is normally higher than the relative full-scale car, and the configuration of this model is big part of this cost, because normally we have balances, sensors, electronics installed. So finally, the configuration that obviously addressed to the target of performance of the car may bring the cost to that level.
What are we talking about? Which cost?
We are talking about, let's say, 250,000 euro to up to 1 million or even more. So the range is extremely wide.
1 million euros for one model.
For the top class, I would say, yes.
Huh. And there is one model. As you can see, it's covered because I cannot show you it, because it's about a car which will come out in 2026. And probably if somebody is watching this video in 4 years, we'll see this car racing in real life. And I want to show you just the thing that I can show you, which are the details. Because when you talk about the model, you think about only the aerodynamics outside, but the aerodynamics is also inside, so they have to replicate everything. The behavior of the car, so active suspensions, and or the air flows inside the air duct, the radiators. Imagine that in the wind tunnel they also simulate, they replicate the exhaust gases coming out at different level of acceleration, because those exhaust gas coming out change the aerodynamic behavior on the car. But not only. Here I have a wheel with the tire and the tire blanket, because they have to replicate exactly the behavior of that tire in the real life. So they design a model also of the tire, which together with all the components, it costs like a Porsche. So finally we are here in the wind tunnel, and how it works.
This tunnel is a closed circuit one, has a layout. We are here in front of the test section. This is the configuration of the tunnel, and the flow is generated by a fan that is in this section, and this fan is connected with an electrical engine with 1000 horsepower. Top speed is 64 meters per second, and the speed is for the flow and for, let's say, the moving belt. When the model is testing, it can rotate around the 3 axes automatically, so it can automatically roll, yaw, pitch, and steer, because we have an electrical engine running the steering. So in a few minutes we can get all the aerodynamic data of the car, this in terms of a map envelope on the road or on the track.
So we are in the wind tunnel. It's amazing to see it. So this is where the air comes from, and as you can see down here, it's written "do not step." And I asked them, what happens if I go there? I will not be able to come out. It looks like a trap, but yeah, if I fall there, they will have to take me out with the ropes. So the air comes from here and hits the model, which is behind there. So we have a model inside. We cannot film it, even if it's covered, we can't, because it's super, super, super top secret. In fact, we put this thing in the front so that it covers it. But what basically happens here is that you connect the model to an arm, okay? And when you test the car in the wind tunnel, the arm pushes the model down and it makes it touch the moving belt. Okay, we have a belt here which is moving at the same speed of air, but be careful, the model must not touch the belt, only the tires have to touch it. So why do we have this moving belt? Because we have to simulate, to replicate the asphalt flowing down the car. So this moving belt goes at the same speed as the air. So if the air goes 150 kilometers an hour, the belt moves 150 kilometers an hour. So why did I say that the model should not touch the belt? Because if you touch it and it breaks it, the belt breaks, the model breaks, and we're talking about hundreds of euros of damage. So it's very important not to do that. And during each test inside the wind tunnel, they put the tire blankets to keep the tires warm and replicate as best as possible the deformation of the tire. And have you ever seen those videos of the wind tunnel with the smoke flowing on the car? That's science fiction. That's not what happens in reality. They don't use the smoke. They just put some sensors inside the model which measure all the forces and the pressures and everything. And as you can see here, the walls, the sides of the wind tunnel are made of these plexiglass parts which have holes because they have to let the air deflow and not to create difference of flows and pressures inside this part, because the air flowing through the model must be as clean as possible from any vortex or other things that disturb the flow.
I am speechless. The amount of things that I didn't know and discovered here in the aerodynamic part is unbelievable. Just the fact alone that in the wind tunnel they put a car to scale. Did you know that? Time to say goodbye to the Alma and to thank him very much and to head to the next building. So far we have seen how to design the aerodynamic of a car, so the form, the shape. But what about the substance, the structure, the metal and the carbon?
Welcome to the DARC! DARC stands for Dallara Advanced Research Center. Here with me is Luca Vescovi, who will guide us through this area. And what do you do here?
So we are basically researching for new ideas, new concepts, new materials.
Okay.
You see in this area of the DARC, we have all the colleagues that are working on structural calculations. So they are basically 24 hours a day calculating from structural point of view our components. So all the components on a racing car, also hypercar by Dallara.
So they build a virtual model of the component and they test it virtually?
Yes. So it's called FIA method. We check from structural point of view all the components virtually in order to come to the prototype with, let's say, sureness of what we are designing.
So this is the kind of the brother of the CFD from aerodynamics?
Yeah, very similar.
Same idea?
Yeah, yeah.
Okay.
With the idea of seeing the structural properties instead of seeing the aerodynamics property, yeah.
Okay.
Okay, here you see, for example,
roll bars?
Yeah, yeah.
Whoa.
You know quite well. So a lot of history of roll bars.
I never destroyed one, but I hope oh, look at this.
These are all tested in-house.
This is not an actual crash.
No,
you tested
no, exactly. We have to test them with FIA, with the regulation guys, and we test the properties that we got on simulation to double check that everything works. Obviously, this is a very safety critical component, so very important. And for example, you see passing from the technology of composite material through metal.
Okay.
And today Formula One or similar, a lot of them are based on metal back.
And on the other side?
Okay, the other side of the office is basically completely dedicated to research. So here we are basically thinking what will happen probably in the next 5 to 10 years. Nobody knows, but you try to forecast. And so you try to push on new technologies, new materials, new ideas, new method how to design parts.
Yeah, so somebody told me that you are researching on new fibers instead of carbon.
Yes, also. For sure. The reason is that, as you know, carbon fiber is very, let's say, demanding in terms of energy, in terms of CO2 emissions. It's a fiber very important for racing market, but anyway, we need to research new solutions. Although they cannot be applied directly today or tomorrow, for sure this is a thing that we have to follow. This, for example, is flax. So it's flax fiber, natural fiber.
Is it the same as my shirt?
Your shirt.
Really?
Yeah. The only difference is that there is resin also.
You can really make a race car out of my shirt?
Yeah, we will try. Not yet.
No way. It's like carbon.
Yeah, it's quite stiff. Obviously, it's a natural fiber, so the performance are not
Behind this carbon.
Yeah,
Okay.
behind this carbon. In this case, we have also parts that are completely in flux. We are checking this not for primary structures, but for body panels, interiors, whatever we can. Obviously, it's a great step forward to get somehow a fiber that, although it has less performance, can be used in our parts.
Okay.
And for example, very related to this, we have also recycled fibers, carbon fiber in this
You
case.
recycle carbon.
We don't recycle, but we use recycled fibers. And so also in this case, you have a chance to give a new life to carbon fibers that have already made their job in long fiber, continuous fiber. So they are chopped and they are again mixed with resin, and we can use for secondary targets, so not with the same performance of the original one. For example, if you have to make a louver or something that has a lot of loads, you can directly use this chopped fiber that is recycled.
Structural.
Yeah, right. This is already a body part, a side pod of our USA car.
In the car?
Yeah, in the car. It was a test in flux to understand the stiffness and also the weight, because the flux fiber is lighter than carbon, but obviously the performance are lower.
Wow. So we went downstairs and it looks like a surgery room.
Yeah, they are quite similar because they are, let's say, clean rooms where the air is changed every few minutes, because we have to be sure that the polymer, when it's not cured, it's completely without any dust, any grease and so on. Example, my colleague is repairing a monocoque chassis after some races, because it's very typical that they have big or small damages. And
Maybe he either a crash or they hit a curb too hard.
Right.
Wow.
So they hit very often too hard the curbs, and the keel, the air of the keel of the monocoque is damaging, and we have calculated and then designed reparation strategies for every damage.
Okay.
Going on, we have a lot of different rooms that are specialized in single activities.
Okay.
For example, preparing surfaces with sandblasting with primerization.
Okay.
Or let's say preparing the molds for the loop of production, so with release agent and all the things to prepare the surface, because obviously the parts have to be detached from the mold, so they have to be released.
With hammer.
Yeah, the release anyway happen also with the hammer. So
really?
in this area we can use the hammer, although if it's well designed, the hammer is not so needed.
Because I heard somebody hammering before.
For sure. And then we go to the heart of the curing process. That is also a relation with formulas. That is the autoclave.
This is like a big oven.
Yes, it's a sort of oven with also pressure. So we have only a temperature and also pressure.
So the part is put inside not only at high temperature but also at high pressure.
Yeah, right.
Like what? How many atmospheres?
Like up to 10 bars, normally 6, 7. And then there is vacuum. So you see all the vacuum lines that are needed to polymerize the parts.
Okay, it's huge. And inside here they are cooking a hypercar. A new model which is not yet there. Unfortunately, I cannot tell you which one exactly. They told me, but I can't tell you. It's a wonderful hypercar, trust me.
Then there are other processes, and for example, you see a small press. We have a bigger one in the research area that is needed to apply the same approach, so temperature and pressure, but with very high rate of production and thermoforming the part also from flat stack, so without pre-lamination.
So sometimes the carbon part can be cooked inside the autoclave or it can be pressed.
Yes.
The difference is that here it's more resistant and structurally, but here it's quicker to be made.
This is quicker and you can get the same level of performance, but obviously the shapes have to be designed for the process.
So in here you put the carbon parts, which are manufactured here.
Here, inside we have a small clean room, small because here we are just making prototypes and not production.
Okay, so the production is in Collecchio.
Right.
Here you just do the prototypes.
The prototypes, but it's done in a clean room where the colleagues are laminating by hand the components.
Clean room, it means like the cheap productions where they have to be super clean.
Yeah, they have to be super clean, obviously, with some limitation for us.
Okay,
because
not that clean.
No, not that clean, but anyway, super clean for the polymer.
Okay.
Because when the polymer is not cured, can be attacked by a lot of chemical elements.
Because, for example, if dust or fat or oils get into the polymer,
It's a problem. Yeah.
Okay.
Now my colleague Irene is, let's say, laminating by hand a component on the mold. This is a very, let's say, tailored activity. So she has to know how to drape the materials, and she has to stack all the layers that are required from my colleague of the virtual development.
So when you see a part made by layers,
Yeah.
so it's actually layers of carbon. So she puts the layer one by one,
Right.
maybe inverted depending on the
Different
requirements.
angles, yeah.
So the guys on the first floor, they
Yeah.
test it virtually and they say, okay, this part should have 6 layers.
Yeah, right.
So she puts 6 layers.
Resin is inside
Okay.
the material already, so it's so-called pre-impregnated.
Oh no, guys, look at this.
Oh, okay.
Could I touch it by hand?
Yeah. This one you can touch. Normally you cannot touch the resin
Okay.
of the pre-impregnated because if we put grease or everything that can detach the resin or create problem to the resin, then there is a problem. So normal, we will put it in the trash.
now.
Yes, it's
No,
waste.
sorry guys, but look at this. This is like,
Your T-shirt.
yeah. And the thing is that it's sticky. That's because it's full of resin,
Yes.
and when they will put inside the oven, it will cook.
Yes.
Wow.
With the pressure and temperature. Yeah.
Wow. There are holes.
Yes, there are holes, let's say, between the bundles of the fiber. So this is normal, and it's depending by the fabric shape, let's say.
Okay. So inside here we have the part that she manufactured. It is put inside this bag, and then
And then you apply the vacuum
Okay.
through the breather, that is TNT. Through the breather, the vacuum can be applied until, let's say, the vacuum bag has completely given the same shape of the mold. So inside here you have the mold and the part, and the vacuum bag will push the complete mold shape.
And then when it's under vacuum, you put it in the autoclave.
Perfect.
Wow. Okay, so I cannot show you, but inside here they are building a part of the Haas Formula 1 racing team. I mean, it's just a pink plastic bag, okay? It's not that you see anything, but... Earlier we were upstairs, now we're here, and this is the research area. We have, for example, this huge robotic arm which is able to do many stuff. A hand bike like the one of Zanardi. We have some parts of the Dallara Stradale. Probably the foreign people don't know who Zanardi is. He's like an idol for us Italian race driver who crashed in the IndyCar. He lost his legs, and after that crash without legs, he came back stronger. He won the Paralympic Games on the handbike, and then 2 years ago he had a bad crash on the road. Now he's not good. He's recovering, but it will take long. And meanwhile, Dallara is developing the handbike. He trains bees. Guess what it is? Come on guys, it's easy. Look at the shape. There's not even need to tell you. So it looks like a finishing area.
And it is a finishing area, you're right. So although we try to design better and better, some action of finishing, of bonding, and let's say assembly and control are needed. And so this is the area where we are doing all this.
I'm trying to find the strength to get inside, because is that the temperature?
Yeah.
Okay.
We have an area that is at 0 degrees, that is at the frosting,
Oh.
and then the real area is at minus 18, that is where we have to store the materials.
So you store everything in minus 20?
Yeah.
And then you move it to 0?
Yeah. To start the defrosting.
The defrosting, and then you take it out.
Yeah, right.
Okay, can I open?
Yeah. So here you are at 0, so it's quite hot still.
Hot? Where? Oh my.
And then
So
you
this is
finally
0.
reach the marmolada minus 20.
Okay, Alaska, here we come. Oh. Oh. No. Come out. Oh, now the 0 degree looks like Maldives. It feels stay at the beach,
Yeah.
drink a mojito. Okay. So this room looks like Matrix, and what is that?
This is the company data center. Starting from here, we deliver all the ICT services for all the company of the group.
Okay. So it's not only data, but you also do the calculations in
Yeah,
here.
we are doing calculation every day, 24 hours a day, from structural analysis or CFD.
Okay. So for example, the guys developing new parts and testing them virtually with the models, they prepare the model and then they send it here to do the computational stuff inside.
Yes, of course. After a lot of calculation, the system provides a solution in order to see the behavior of the car in terms of structural analysis or computational fluid dynamics analysis.
Okay. Also for the CFD,
Also
for the
for the
aerodynamics.
CFD. Yeah,
Okay.
of course.
Wow. Can we get inside?
Yes, of course.
I'm a software engineer. Whoa! there is a storm in here. Can you hear my voice? I really struggle to talk to. Wow, that's so loud in here. As a software engineer, I love this kind of stuff. Wow.
Okay, since talking in there was impossible, I will summarize one very interesting thing they told me. These servers heat up like crazy, obviously. And they're going to consume a lot of energy to cool them, right? Well, actually no, because this whole system has been studied in great detail to minimize waste. This monitor, for example, shows the total energy consumption, which is 526 megawatts per hour, total of which 517 is to power the servers. That means that they consume less than 2% of the energy to cool them. With that sound still ringing in my ears, I say goodbye to my guides and I get ready to discover the simulator, the composites, the machine tools and the testings. But first, I want to go back to the academy where Gianpaolo Dallara and the CEO of Pontremoli are giving the end of the year speech and giving Christmas gifts to the employees. The thing that struck me is that some of the gifts are not only for the employees, but also for their children, for their family. Yeah, because here it's like being in a big family.
Appassionato, no, di motori, conosco cose Dallara, ma non avrei mai immaginato di trovare quello che ho trovato quando mi sono state aperte le porte per entrare qua dentro.
E in compenso né io né tu riusciamo a immaginare quello che sarà domani, se non che sarà ancora più entusiasmante, che sarà diverso, che continuerà ad appassionare e sarà da reinventare sempre.
Cos'è che l'ha portata a passare da un'azienda enorme come l'IBM a una realtà come Dallara? Qual è la cosa che l'ha spinta?
Ma le motivazioni sono tre principalmente. Una è che io sono cresciuto su questo fiume, decido un bel giorno nel 2007, l'alba dei 50 anni, di ritornare nella mia terra e Gianpaolo Dallara mi dà questa possibilità e qui c'è la seconda motivazione. La prima è per tornare a casa, la seconda è perché Gianpaolo Dallara mi ha dato la possibilità di provarmi da imprenditore. L'azienda allora era 107 persone, pian piano oggi siamo 740.
In 15 anni?
Sì. L'altra cosa che è importante per me è il fatto che io ho sempre avuto la passione delle corse, correvo in moto perché non mi potevo permettere le macchine.
Ne so qualcosa, ma guarda che è incredibile come gira, arrivi sempre lì.
Ecco, queste sono le motivazioni che mi hanno portato a venire qua.
Wow. L'obiettivo che ci siamo prefissati con questo documentario è quello di far vedere tutto il lavoro che c'è dietro un'auto da corsa, ma non solo, le persone che ci sono dietro, quello che lei è stato in grado di costruire in questi anni. Io sono convinto che quando uscirà questo video tutte le persone che passeranno qua davanti e vedranno scritto Dallara sapranno davvero la magia che accade qua dentro.
Ma la magia vera secondo me è essere circondato da un gruppo di persone che sono cresciute insieme a fare questo bel mestiere, a continuare a imparare e che hanno il piacere di continuare a crescere in competenze e di provare anche sbagliando a fare delle cose nuove. Perché il detto sbagliando si impara anche all'epoca dei computer ha ancora senso.
Sì. La ringrazio, ingegnere.
Grazie a voi.
Ci vediamo. Verrò a trovarla nel suo ufficio poi.
Con piacere.
La ringrazio molto, è stato un piacere. Continuiamo il nostro giro perché ho mille cose da scoprire e da raccontare. And so a company like Dallara, who designs and manufactures and produces some of the best race cars in the world. How could you think that they don't have a driving simulator? Yeah, that's it. Look at how huge it is. This is the driving simulator of Dallara. And if you think that they use it only to simulate the drive, it's wrong, because this is used to help the Haas Formula 1 racing team during the racing weekend. Because, for example, in the Formula 1 Grand Prix, Haas just finished the FP1. They have to change something in the car. So what do? They call the team here in Dallara, which replicates the conditions of the actual racetrack. They do some sessions on the simulator. They have some control room upstairs who analyze all the telemetry, and they suggest possible modification to the team in real time during the Grand Prix. And I will make a detailed video about it because my career started from the simulator, so I want to dedicate a whole video about it. But the amazing thing is that this is the cockpit of a prototype that I will test on the simulator. And when they have to test a car in the simulator, they change the cockpit physically. They put this on the simulator. So that you're not just testing the car virtually, you're actually sitting into the real car inside the simulator. Same condition as the real world.
Since my journey in motorsports started with simulators, I couldn't resist in trying it, so I had the honor to get into it and experience it for myself. That's going to be super cool, so I will make a dedicated video, which you will see soon on this channel.
So we moved out of Dallara a few kilometers and we came to Dallara Compositi, which is the headquarters of production. So do you remember the dark where they do the prototypes? So those prototypes, once they are ready to be produced, they get produced here. And there are many pictures of many cars here, and I told you that Dallara makes components for other cars, but as always I cannot show you them, so the only thing I will be able to show you is the Dallara Stradale. So now we will see how we transform a sheet of carbon into a chassis. So we are here in Dallara Compositi with Davide Seletti, and Davide, what do you do here?
Yeah, we do many nice things and all in composite materials, and we do both work for Dallara and other OEMs.
Okay, so every composite component starts from here, from a simple sheet of carbon.
Yeah, I mean, it's quite strange if you look at the final product, but everything starts from a roll. The roll is frozen, needs to be defrosted, and then is cut by machine, and then every single ply is put on a mold by an experienced laminator, so that in the end we get to a final product. So every single, let's say, the small patch of carbon is made of 12,000 single wires. So it's 12,000 single wires for each single carbon fiber patch.
And there are different sizes.
Yeah, you can go from 1K up to 80K. Usually it's 12K, but I mean aerospace standard grade is 6 to 12K.
Okay.
And this is in this case T700 grade.
So the less wires, the bigger the wire, the better.
No, the bigger, the less the cost, because you can do lots of weight in a very small amount of time.
Okay.
With 1K is very, let's say, small patches, so it's very close in terms of weave, so it's very expensive to go.
Okay. So we get to the laminations, all the sheets of carbon that have been cut, they get put together here in the stamps, right?
Yep, I mean, what we are in here, we are in a clean room, so we are laying up the Dallara Stradale. We have two molds. On one side we have the two sides of the Dallara Stradale, on the other side we have another mold where the wall of the Dallara Stradale is being put together. So every single ply of carbon is laid up following a ply book that gives the instruction of which ply to put in which stage, and then it's all hand lay up until a stage where the two sides and the bottom are put together. So on here you can see at the final stage, because the car comes as a monocoque, so in the end is put together both the two halves and the two sides, but also the bottom, so we go curing in one single chassis.
So this is the beginning of the chassis, and that is almost the end. And I have a nice anecdote. That girl down there, she's one of the youngest in here, and her mom does the same work here, just in another office. Okay, so all the sheets that have been laminated, now they are closed in this bag, ready to be cooked, right?
Yeah, what you see at my left-hand side is a Super Formula chassis that is being finished to be cured and will go to Japan for the Japanese championship.
So how many man-hours of work? there are right now in this part?
We are in the range of hundreds of man-hours, because I mean it's a very complicated chassis and with a high-performance chassis, so there is a lot of work to position every single patch of carbon up to this stage.
A mistake in the bag here means throwing away everything.
It's something that might happen. If it happens during the early stages of the cure cycle, it's something that can be repaired, because we have, we measure the vacuum, so we know if something is wrong. If it happens too late, you have just to hope that everything is fine, but sometimes it's not.
So this is the bags area?
Yeah, this area is the one before curing. So the components, small ones, are laid up in the clean rooms, and then I brought in here to get put within a vacuum bag. That is the final stage before the curing. So any component needs to go into the bag, so every ply is pushed one against each other and everything against the mold. And then every component is laid up and left in there. So you can see different colors. Different colors means different bags. Different bags are used for different curing cycle. The blue ones are for high temperature curing.
So do you remember the autoclave from Dark? Imagine them bigger and more. There we are. They produce lots of parts here, so they need bigger autoclaves. So after being cooked, the parts are taken out of the autoclave. They remove the plastic bag and...
First you demold, so you take the component out of the mold, and then you go trimming or machining. So when you get the component at the final shape, it's brought in here, whether it's assembled or bonded. In this case, we have...
Is it what I think?
Yep. It's a Formula 1 wing from last season, so it's the new regulation. And this wing had a bad encounter with something stronger on the left-hand side, so we had to remove an end plate and put a new one. And this was ready for the final race, should it be needed, but there was no need, so we didn't ship.
Wow. If you don't know where to put it, I have room in my house.
It's not mine, so you should ask the customer. And here you can see a front end of a landing BH car for next year that is being final assembly to go shipping for the customer.
Which car?
I can't say, sorry.
What's he doing with that laser gun?
He is scanning a carbon fiber component. The component is being laid up, put in a bag, cured, demolded, and then after the trimming step, before it's either bonded or delivered, we have to scan the surface and everything to see whether it's done as it should be.
So what's going on there?
Here we are with the chassis of the Dallara Stradale that is being laid up, cured, demolded. Already had the first primary bonding. You see the roll-up cover behind the drivers and the passenger head, so all the fairings there is bonded. And then we go machining, so we have to drill through any kind of holes, make planes, make references, so that after this we can attach, bond or do anything to the chassis before we go to the assembly line.
But when you talk about attaching, you mean glue, using the glue? The actual glue?
Yeah, it's aerospace standard glue. It can put together a Formula 1 wings like the one we saw before.
Wow.
So if it can survive the Formula 1 environment, it will survive very well in the road car assembly.
The glue. So for example, here you can see two parts that still needs to be glued. So at the end of the process, we have here the products almost ready to be shipped. Here we have the chassis of an LMDH, the Cadillac, which is the one that I will drive on the simulator. And this is the Dallara Stradale chassis, almost ready to be shipped to the factory, where it will be assembled into the final car. And the chassis comes here to the Dallara Stradale warehouse, where the final car is assembled. We have a production line where all the parts come here. They are assembled and we go from the parts to the final car, ready to be delivered to the customer.
So, in your opinion, could I not try it on track? Of course not. The way they build this car is simply amazing. So, also about this car, I will make a dedicated video that we'll see soon on this channel.
So you're probably wondering why we're filming that house down there, because that is the house of Gianpaolo Dallara, which is right in front of the warehouse where they build the Dallara Stradale. So you may say, okay, why did he buy that house? He didn't buy that. He was born in that. That is the house where he lived his whole life. And the incredible thing is that every time he opens the window, the thing that he sees is the production of the Dallara Stradale. And this is the true meaning of passion. Building something this big, something this wonderful, something this amazing. And after a whole life working on cars, desiring to wake up every day and see the production of the car that you designed and built.
A company is like an orchestra. You can have the best musicians in the world, but if there is no good conductor, the orchestra will not sound good. In Formula 1, this figure is called technical director, while in companies usually know him as CTO, a figure that here in Dallara is held by Aldo Costa. We're talking about one of the best CTO in the world, a man who has won 26 world titles in Formula 1. Ferrari Formula 1 Technical Director from 2008 to 2011, Mercedes Formula 1 Technical Director from 2011 to 2018. I had the pleasure of talking to him for a few minutes, and I wanted to ask him what exactly does a CTO do?
You are the CTO of Dallara Group. So what do you actually do in here? What does the CTO do in Dallara?
The CTO is managing a very big group, very key for let's say the Dallara Group itself, which is the technical direction group. So is the group that is designing, is the group that is as well producing parts, is the group that is delivering what we do in terms of design, production. So we are talking about racing cars, we're talking about automotive activity, engineering work, mainly we are talking about aerospace and defense.
So basically the CTO doesn't do calculation, simulation, or whatever the engineers do, but it's more like he checks that everything works fine. It's like a supervisor, right?
Yeah, the CTO, let's say there are multiple aspects of this function that need to be considered. One is making sure that people has got the correct skill, training, the correct tools, the correct methodologies, so they are prepared to do the job they are meant to do. But what the CTO shouldn't do is doing micromanagement.
Okay.
So he's not a person that is meant to follow the details. He must empower people and give responsibility to people to go ahead with the project, with the activity, making sure that everything is like a big orchestra.
Okay, yeah, it's like an orchestra director.
Everybody are playing, an excellent music, but everybody are skilled and prepared properly, and they've got the right tool to do it.
Okay, so you don't play in tool, but you direct the orchestra.
Exactly.
Okay.
Exactly.
So what is the hardest part of your job?
Yeah, the hardest part is establishing priorities of any kind. You know that a company like us should look after innovation, future new technique, methodology. But in the meantime, we have as well to follow the current project. We have to grow up the people for the short term, medium, long term.
So it's more like management.
Yeah,
technical management.
Technical management.
And if we compare to Formula 1, which are some famous characters who do your same job?
Yeah, where I come from today, we can say James Ellison. James Ellison is the CTO of Mercedes F1.
Okay.
Adrian Newey or any other CTO, technical director of F1 organizations.
Okay. Thank you, Aldo. It was nice to meet you.
Welcome to you.
We saw how a race car is designed and how it's developed on the PC and in the wind tunnel. We've seen how the carbon fiber is processed, we have seen how to build and prepare a chassis, but we have not yet seen how the metal parts of the car are built, and especially how the final car is assembled. This is done in the production area, where Luca Pignacca will guide us. Just think about it. Luca has designed all the Dallara race cars of the last 30 years, and he is responsible for the American NASCAR program. Yes, because of course all American NASCAR cars are designed by Dallara. You didn't know that, right? The first room we see is the machine tool room.
So Luca, what do you do inside in here?
This is our CNC machines department. So this is where we manufacture, we actually make parts, mainly out of metal, so steel, titanium, aluminum, but also we machine some composite components, for example, complete monocoques or wings or front nose boxes. And here we do all the drillings, the tapping, so that the part, the monocoque, for example, is ready to be assembled with studs, bolts, pivots, and so on.
I saw a strange machine with the blue arm. What is that?
Okay, here we've got very good and skilled people, and we rely on their skills, yes, and on their commitment. But unfortunately, these people want to sleep, and they get sick.
So bad, yeah. And, they want to eat sometimes.
Sometimes they stop for eating, and you know, and Christmas time they say, I would like to stay home with my family. And so how can we fix this problem, which is a big problem, of course, yes. Basically, this machine can work by themselves. So overnight, the operator programs the machine so that it can work unattended, let's say. But when the part is finished, someone should remove the finished part from the machine and put a new one on, a new block on the machine. And so we hired a new guy. It's a blue guy.
Wow.
It's a robot, basically. And so this blue guy just takes a small block of metal, puts it on the machine mandrel, and the machine does its job. And when it's finished, the robot removes this finished part from the mandrel and puts a new one on.
Wow. So I saw the Haas logo on this machine and I said, why is that? If you don't know it, Haas, they mainly produce these kind of machines. And then they also created the Formula 1 racing team. So it's crazy how Dallara designs the Haas Formula 1 racing car and builds car parts using the Haas machines. Wow. Vado? Vai.
This is our fabrication department. So here we do all the weldings of metal parts. For example, this is a suspension control arm or suspension wishbone. And these guys here start from simple machine parts like this one. And they assemble it to some tubings, like for example this one. And they weld them, you know, perfectly. They must be highly specialized to do this job. And these wishbones, these control arms, will do 24 hours at Daytona, Le Mans, and so on. So all our cars, but Formula 1, are made out of fabricated steel.
Okay.
The only other exception is NASCAR. So
the American,
the American next-gen NASCAR, which is where we have control arms made out of aluminum. And
it works?
They do work, yes. Actually, to validate these new control arms, we use the cannon. In the NASCAR Technical Center in Charlotte, we tested these control arms using an air cannon, shooting a bullet, approximately 30 kilograms bullet at 180 kilometers per hour against these control arms, because we wanted them to fade in a controlled way. This is our inspection department, quality control. And this is where we check all the components that we make either internally or we buy from the outside suppliers. All parts must be exactly as the design office designed them. And these guys here, their mission is to check that these parts are ready to be either assembled on the cars before being released to the teams, or sent or sold as spare parts to the teams. Here we also check RFIDs inside components like this one. We find the code, or basically the name of this part, so that this part will be followed during all its life. If something happens to this part and must be written off, we know that these parts cannot be used anymore. And if the teams try to use it again, we will catch them. And here we also laser etch parts. So on each part we print with a laser machine, which is over there, the Dallara logo, the part number, and a sort of ID number, so that we can trace the parts throughout the whole life of these components.
Look at how awesome is this part. This is the rear of the LMDH Cadillac.
Yes, the new one, or we should say GTP car, because this is the new name, although we call it LMDH. This is the rear end, as you said, and it features the last part of the underfloor, which we call the diffuser, the rear diffuser, the rear crash structure over there. The red thing is the tow hook. If we want to tow the car, you can pull it. So with a strap, we can pull the car out of a gravel trap, for example. And then the main element, which is the two elements, main rear wing, flap and main element, with a central pillar. And these are the rear lights. Some of them, there will be other lights somewhere else here, but they're not fitted yet. And these are LED lights. We use as running lights as well as rain lights or fog lights, or even brake lights. And if we need to replace this, because if they stop working, you have to stop at the pit and change them.
And change the lights.
But we do not change the light, we change the whole assembly.
Really?
In a few seconds. Changing the lights would mean to lose 5 minutes, for example. To change the whole assembly, it's a 30-second job. So.
Okay, and then the mechanics just change the lights.
Can change the light with a comb in the garage, ready for the next time.
Wow. So how much load can it resist?
A lot of load, because these elements, these wing elements, produce a huge aerodynamic load. But we have to pass a test prescribed by the FIA, and we have to load the main element of the wing with 1,000 kilos.
1,000?
1 ton.
You can put 12 versions of me on it?
Yeah.
What is this mess?
This is the stores, and this is the department of the old Dallara factory with the biggest pressure at the moment. This is the stores. This is where everything comes in Dallara and everything goes out of Dallara. So this is the key department now, really under pressure. So every day these guys come here with the knife in their teeth, in the trench, fighting, trying to survive.
To ship everything in time.
Yes, because you can design the best car of the world, you can make the best car of the world, but then if it doesn't get to the customers, it's useless.
Yeah, it's useless. So this is the halo for Formula 1, Formula 2 and Formula E. Why did I say these three cars? Because these are the only three cars with the titanium halo. And it's quite lightweight considering the amount of metal it had inside. So once the car is ready, what do? We put it in a box, in a huge box like this one, and we ship it to the customer. So once every part is ready, they come here and they build the actual car.
This is where we assemble either sub-assemblies or complete cars. In this workshop, we receive, for example, the monocoque. This is the good old Cadillac LMDH monocoque. And so autoclave, raw parts, no holes, no machining. Go to the production department, CNC department, drill all the holes, do all the threads. Then we hand finish the monocoque. And then eventually we'll come here with all the parts, and the mechanics assemble all the single components on the monocoque. And so this is ready to be assembled on the complete car.
In a car like this one, apart from the engine, the electronics, the gearbox and the wheels, you build everything.
Basically, yes. We certainly design everything, and we manufacture in-house almost every component of the car except the ones that you just mentioned.
So my question is, how do you combine the performance of the car and the design? Because the car must be fast but also good looking, or not?
Absolutely. And this is one of the most difficult tasks that we have to face when we design cars like these. Basically, motor racing is a big marketing tool. So the big OEMs spend a lot of money to advertise their products, basically. And so people must understand that this car is a Cadillac. When the crowd will watch the Daytona race, they must realize immediately that this one is a Cadillac. And the key is to speak the same language of the stylists. The aerodynamics guys at Dallara know exactly what the function must be of a car to be a winning car. And we have to educate the stylists so that they can understand what we need. But at the same time, we must understand what they want to pass to the public. And when you start speaking the same language, then it's easy.
On that chassis you see back there, Dallara professionals will install all the components one by one, until after hundreds of hours of painstaking work, the car finally takes shape. The stunning Cadillac LMDH. just moved to another department, the control and testing area, where the manager Nicola Valeri explains what is done in here.
So, Nicola, this is the Cadillac, the one that we saw all the parts around there.
Yes, right.
Wow. So, it's finished, and what are you doing here?
Yes, it's more or less finished. It's more or less ready to go on track. We are now checking the camber, and the toe, and everything needed to be perfect on track.
So it's like when you do the level with the bubble, you're doing something like that?
Yeah. We are on a flat surface, and then we are checking if all is on level. Yeah.
And then once it's ready, it goes to the US?
Yes.
What is this?
It's a cooling system rig. So it's a sort of a small wind tunnel where we bring air from outside and we pass the air through the radiator. Then we are able to measure a lot of sensors, like velocity of the air, like the flow of the fluid and the pressure and temperature. Using all these sensors, we are able to understand if the radiator is okay or not for our cars.
What is this? 7-poster rig.
Yes, it's a rig for the tuning of the suspension, called 7-poster rig because we have 4 pads under the wheels and 3 aero loader actuators, 2 on the rear and 1 on the front. So these actuators are needed to replicate the downforce, so they bring the car down during the movement of the rig.
So you connect the car to those 3, they pull the car down to replicate the downforce, and they also replicate the braking and load transfer.
Yeah, that's right. Wow. And so we are able to replicate a track profile. So all the movement of the car, for example, when you are on a straight and you are braking, the car is moving like that, so it's pitching. We are able to reproduce that.
Wow. So for example, you can replicate a lap on track in here. And you are able to change the setup to see if it works or not.
Yeah, right. We are able to change the damping of the damper or change springs.
Without driving?
Yeah, without driving.
So for example, in classes like Formula 1 where tests are limited, you can test them here.
Yeah, you can test a lot of track here and see how the car responds to the rig, so how the car responds on the track, because we are replicate the track. Not only racing car, also road car, we can do that. Yeah.
Okay. And about the other?
Yeah, we have another rig there. It's called a corner rig because we are able to apply the loads to a corner, so a quarter of car, fix it to the rig. Then we are able to move this corner and apply all the loads that the car will see on track. For example, we are using to do that, applying a load for 24 hours to check if all the components, so the brackets, the arb, the part of the suspension, are good or not to go on track.
Wow.
Having arrived at this point, after it has been thought out, designed, modeled and studied, prototyped, built, assembled, adjusted and tested on the dyno, the race car is finally ready to be delivered to the customer, fired up and driven. I can tell you that I was literally speechless at what I saw in here, and I hope you were too. I never expected that there was so much sophistication behind a race car, so much magic. To think that from those simple rolls of carbon could come to this. And to think back to the amount of work, research, development and technology behind it, it just left me breathless. Behind masterpieces like these, there is not only machinery, materials and formulas, but there are mostly people. People that I've had the pleasure of meeting and introducing you to, and it was only by talking with them that I realized what the secret ingredient behind Dallara's success is: passion. Building race cars is an art whose brush is passion. Passion so big, the one of the engineer Gianpaolo Dallara, that he was able to involve, train and inspire thousands of others like him and build a company that is unique in the world. If you ever have the chance to come to Italy, come to Varano de Melegari and see Dallara with your eyes. You will know that the magic exists in here. And every time you see a supercar or a race car go by, you will know that there will most likely be something thought of, designed or built by Dallara in there, even if nobody tells you it. Very often you will not know what it is, because it's a secret, but from now on, you will know it's there.